Hello, everybody. Welcome to the special 4 o'clock Wednesday edition of Orgo 1 lecture. I have uncharacteristically some visual here. I have in my possession a lab glove, and my question for you is quite simple right now. Why do lab gloves only come in one box when we have two different hands? And well, it's because we can get this glove on this hand like this, right there. And we can get the same glove. How do you get it on the other hand? Clearly it has a thumb, an index finger, and a pinky. Oh, I flip it over and I can get it on the same hand. Okay. So have you answered my question yet with our new words in chapter 3? The new words I want you to think about are, well, there's only one. It's chirality. All right. Now these gloves, they look like mirror images of each other, but in fact, they're exactly the same, and I can get each one on each hand by just flipping it over. Now I have these much nicer gloves. These much nicer gloves here. I don't know if you can see that. They're nice. And these are Canadian gloves worn by the Mounties. And I can get this glove on the left hand. I try to get the same glove on the right hand. And well, I need my thumb where the thumb is, but oh boy, that's not working for me. Yeah, it's not fitting properly. Why? Well, it's because it's not symmetrical. I put these, they're mirror images of each other here, but then I try to put them on top of each other, and I got a thumb underneath a pinky. I can get the thumb under the thumb, but then I don't have the top part here and the top part here. They're mirror images again. They're not superimposable. That means these gloves are, and I hope you've had the word chiral in your mind, and these gloves are achiral. So that's why we only have one box of gloves. Finally, we answered that question. All right, I have another question for you. Why is chirality even important? We just finished discussing at the end of last lecture that chiral molecules, the two enantiomers, and I always use my hands because those are perfect examples of enantiomers. The two enantiomers have almost every physical property the same. So why would it be important to know the difference between them? And the answer is quite simple. One important thing that chiral molecules do differently than each other, the enantiomers, is that they interact differently with other chiral molecules. Just let me go back to our glove here. This glove's designed, let's just think about it in terms of biochemistry. The perfect analogy is this is an enzyme, and there's a reaction going to happen inside there if a molecule gets in there. And this would be a molecule going to undergo a reaction. Some of you know that word for that molecule is substrate. So this reaction will happen if it fits, and it fits, so my left hand would undergo an interaction or a reaction. And the right hand doesn't fit, so the right hand just tries to get in there and bounces off. Nothing happens. Doesn't have the right fit. Well, this is because enzymes themselves, which are the catalysts for biochemical reactions, enzymes themselves are chiral. And the right substrate can fit in, and the other hand won't even fit in. And more importantly, if we're talking about a drug, one enantiomer might fit into a enzyme that causes a beneficial reaction, and then the other enantiomer won't fit there, so you won't get the benefit from that enantiomer, but it will fit maybe somewhere else and cause another interaction or another biochemical interaction. And sometimes those things are negative. And when those are negative interactions, we are not allowed to even sell the other enantiomer of the drug. And later you're going to learn that sometimes your body can transform one enantiomer to another, such as is the case with thalidomide. So even if you had the correct enantiomer to start with, your body sometimes can invert a stereocenter and cause the other enantiomer to be created. So we have to be very careful with drugs. We'll talk more about that as we go through today's lecture. So one thing that enantiomers do that's different than each other is interact with other handed molecules like enzymes. And another thing they do that's different is something we can easily test in the lab, and it's how they interact with plain polarized light. So I'm going to focus this whole segment on that, and it's going to be a little bit of a long segment, maybe up to 30 minutes, but it's going to get us ready to answer a very important question on our next exam. So we're definitely interested in that. So we're going to go share our screen now. And I stole some images from the book, and the subject we're going to look at right now is called, if I can get my pen to work, my pen has stopped working. It's not, let's see. It's on. There, finally. This topic is called Optical Rotation. And it's something enantiomers do that's different than each other, and it can easily be tested in the lab. So first we have to do a basic primer on light. Even if you haven't had any experience learning about light, most of you know it travels in waves. So here's my lame attempt at an eyeball, and here's one wave of light. But light doesn't just travel in one waves. With this plane, this is a plane, the sheet of this page, or the plane of this page is here. And I showed that plane of the light here. So this is just a representation of the plane this eyeball's looking at. Here are other planes, and if you break it down, there's almost infinite number of other planes going on in there. All right, we have to filter this light so that it is what's called plane polarized light. Plane polarized light. So you run it through a plane polarizing filter, such as those found in expensive polarizing sunglasses. And the reason they work so well is they get rid of all the planes except for one. And what comes out after the filter is just the single plane. Enantiomers interact differently with this special light called plane polarized light. So what's going to happen if we shine this plane polarized light, which is the light that came out the other side of this filter, we shine it through a sample containing a chiral molecule such as R2-butanol. And then we have a machine on the other side that measures which orientation, a detector on the other side that measures the orientation of the plane. We see here that it got rotated. So this is something that all chiral molecules do. They rotate plane polarized light. And this particular isomer of this molecule rotates it under these conditions with a rotation of the plane by negative 13.52 degrees. That's a property of this molecule. And its enantiomer, I promise you, rotates light under the same conditions at positive 13.52 degrees. That would be S2-butanol, the enantiomer of R2-butanol. And you could look it up, as my students in lab already are doing, but they haven't looked this up yet, in a catalog such as the Aldrich catalog or the CRC index. And you can look these values up. They are properties of molecules. What kind of molecules, I ask? We already said it. Only chiral molecules do this. The rotation of achiral molecules is absolutely zero. Okay, so we've got to learn how these values are reported. Then we have to learn what happens if we do our values under conditions that are not what we call standard. And the standard conditions are as listed down here. A reminder of standard conditions is here, but everything we need is here. The concentration units used in these experiments look like density units, don't they? But if you think about it, density is a measure of concentration, how many grams of your substance in how many milliliters of solution. So that's the units for concentration that we must use. The path length, a standard path length under standard conditions is 1 decimeter. We don't use decimeters very much in this country. So you just got to have 10 centimeters in mind. Remember, that's 1 centimeter right there. You got 10 of them. It's about right there. Okay, there, put for my reference, my head is here. So there you go. That's about 10 centimeters. Okay. All right. So what's going on here is under these conditions at 20 degrees Celsius, you get this value, negative 13.52. So standard conditions are 1 gram per milliliter, 1 decimeter path length. This I wouldn't worry too much about. That is the wavelength of the light used in the experiment. Don't forget, you need light. If you're gonna plane polarize it, you better have light to start with. Okay. This is the D line in the sodium spectrum. I think you might remember the experiment where in chemistry 1, you looked at the lines of the spectra of things like hydrogen and mercury. And you may have done sodium, which is like an orange color, and 589 corresponds to that. And 20 is the temperature at which the experiment is done. Okay, so far so good. Let's answer some preliminary questions. Based on what we know so far, and one fact. This is a good fact over here, that the more molecules that the light encounters, the higher the rotation. So if there's twice as many molecules, you'll see twice as much rotation. If there's half as many molecules, you'll see half the rotation. Each molecule contributes to the rotation. So under these conditions of 1 gram per milliliter and 1 decimeter, if I double the concentration, that'll be twice as many molecules in the same volume. I would predict the rotation would be 2 times negative 13.52. So the answer here would be 2 times negative 13.52 equals negative 27.04. We'll use nicer numbers on tests because we're not allowed to use calculators. Now, if you change the concentration back to 1 gram per milliliter, standard concentration, but now you use a tube that's twice as wide, so it would go to about here. That's 20 centimeters. Then you would have, once again, twice as many molecules. You'd encounter the same number of molecules in the first 10 centimeters, and then that's that amount again in the next 10. And I expect negative 27.04 once again. All these answers are at the bottom of the textbook page. You don't have to be able to read them here very well. In 3, we're doubling both. So when you double the concentration, it went up to 27.04. We're going to double that again. It's going to go to negative 54.08. The next question I already gave you the answer to. These square brackets, I didn't mention it yet, but they mean specific conditions. So you were told the specific conditions for this molecule gave negative 13.52. We have the question now, what would be the specific rotation for the enantiomer? And that is the easiest question here, isn't it? Positive 13.52. That is a physical property of enantiomers. I will say it verbally one time. Enantiomers rotate plane polarized light in equal amounts, but opposite directions. There we go. All right. Now, who remembers the word for a solution where you have equal amounts of two enantiomers, R and S? Because that's question 5B. And from the other day, starts with an R and ends with a C. Could do a hangman here. We usually do those in class for fun. We're not in class, sorry. It's a racemic solution. I hear students say racemic a lot. It's okay. It's racemic. And then if I have a racemic solution, that means I have as many molecules rotating light that direction as I do rotating light the other direction in the same amount. By the end, when the light hits the other side, it will be a rotation of 0. So a racemic solution always rotates light like there's no chiral molecules in there. We know there's chiral molecules in there because we put them in there, but the machine doesn't know there's chiral molecules in there. So we're going to mathematically determine what we would predict the observed rotation to be from the specific rotation in questions 2 and 3, or 1, 2, and 3, highlight it nicely. If you have an observed rotation, a standard rotation, what did you do to it to predict what happened when you went from 1 to 2, which is 2 times 1, right? You doubled it. You doubled this number, which was here, which was the specific rotation. So that's the concentration. You take the concentration, units understood to be what? Grams per milliliter. And what did you do when you doubled the path length? Well, you multiplied the change, the doubling, by the specific rotation here. This is question 2. Okay. Whoops. That's not a good equation. I don't know if I'll be able to move just this. No, I didn't think that was going to happen. Just write small here. The prediction of the lab value will be the specific rotation of the specific rotation for the sample, which is the literature value. Reminder, alpha observed is the observed rotation, experimental value, lab value. I'm going to use those words interchangeably, so I don't want anybody to be lost there. If you want to predict this, pretend you're the machine, then you would multiply the specific one times C times L. But we're not pretending we're machines. Our goal is to be able to use results given by machines to tell me how much sample is present of each enantiomer. That seems like a useful skill, especially noting what I said about, we need to know exactly which enantiomer of a drug we're giving, or else there could be problems. So it's good to know exactly how much of each there is. So you want to reorganize this to get the specific by itself. And I'll steal a little room from the right here. These notes might end up being kind of small. We'll see. This is just straight algebra. Both of these equations will be repeated on the next page. You take the observed rotation and you multiply both sides, divide both sides by C and L to get this by itself. And there you go. So this is how you would predict what the standard rotation should be from lab results. Lab results are almost never done under standard conditions. That does not prevent us from predicting what they would be under standard conditions. And if we're going to use literature values, we need to standardize our lab results first. Now, If I have a mixture of two molecules that are enantiomers that isn't equal, what's going to be my observed rotation? Well, here's how I think of this question. Every one of these molecules of the S enantiomer is canceled by the R enantiomer. So 250 milligrams of S is canceled by 250 milligrams of R. So we're going to have a solution that behaves like there's only 500 milligrams of R in there. Okay, so we say excess equals 500 milligrams, and tell us what chemical is in excess, the R one. So my prediction here, under standard conditions where there's 1,000 milligrams in 1 decimeter, we get negative 13.52 for this molecule. We saw that right here. We have half that amount, so we're going to get half of negative 27.04. Now I got to do some math. Half of negative 20. Can I just go without the decimal just for fun? Half of negative 27 is negative 13.5. You want to go 13.52? That's fine. I won't make you do any second decimal math here. So I would predict this to rotate negative 13.52. And then we've got a question here. Percent enantiomeric excess is defined as how much more of the major enantiomer you have than the minor. What is the percent EE? Well, I have 500 milligrams more excess, and the total milligrams in the original question was 1,000 milligrams. That's 500 plus 750 plus 250, sorry. Make it a percent. 50% EE. What's EE stand for? Enantiomeric excess. Don't invent your own definitions of EE. It's how much more of the major enantiomer there is, in this example, R, than the minor enantiomer.
Excuse me, doctor.
Yes.
Can you just go over 8 one more time, please?
Go over 8. Okay, I have a solution where if you put it in different words, 250 milligrams R and 250 milligrams S is racemic. That would give a rotation of 0. Racemic solutions give a rotation of 0. But there's 500 milligrams extra of R. This is not the total amount of R in that question. There's 500 milligrams more. So this solution behaves like these two things aren't there because they cancel each other. The machine will not be able to know those are there canceling each other. The machine will know that there's 500 milligrams of R not being canceled by anything. And it will behave like a solution where the concentration is 1/2 gram per milliliter. Maybe that's what lost you. 500 milligrams is 1/2 of a gram. We must, all of you must be able to go milligrams, grams, back, forth in your sleep. I tell the students in this in lab, if you mess the decimal up by even 1 decimal place, you're either overdosing somebody by a factor of 10 or underdosing them by a factor of 10. So as soon as I say 500 milligrams, from this day forth, I want you to say, that's 1/2 gram. because in the lab, all of our doses are in grams. Sorry, in the lab, all our balances are in grams, and in drugs, all the doses, almost all, are milligrams, and you have to be able to measure out the appropriate amount. Now, I don't know if I answered your question, but I hope I did.
My thing wasn't the 500 milligrams. It's just because it's R, it's negative 13.52.
That's
Even if,
just a property of R in this example. Yes.
oh, okay. So the
You would
five,
have to be told the specific rotation of a substance before you start any of these questions.
okay.
I'm not making you memorize those. I'm sorry. I hope what I said wasn't a waste of time. I think if it was just one little thing that helped you through, the other parts weren't a waste of time, were they?
Thank you.
Okay. I think actually what we're going to do is we're going to do a problem on the next one, but I think we start the next segment with it. Maybe this would be a good time for you guys, if you want to work on it during the break, do like a screen capture if you can. If this is on your phone, you can do print screen if this is on a computer, and I'm pretty sure this would just be there, and then you could copy paste it into Word or something. So I'll leave it here for just like 10 more seconds, and we'll be picking up right here. The two main equations we're going to use are this, and this is a reorganized equation that standardizes the observed rotation. You take a lab value, multiply it by C times L, and this is a comparison of the standardized observed rotation over the reference rotation, which is also under standard conditions, to give us percent EE. And then we're going to use percent EE to figure out exactly how much paclitaxel is in this question and how much of its enantiomer is present. So that's where we're going to pause, and I will see you in 5 minutes.